Sorry for that. Okay, so yeah, the thing I was saying supports Optimade in the fact that it was decided that it's important to expand Optimade for classical molecular dynamics and trajectories. Okay? So this is something that is ongoing and biosimulation. So we have a postdoc that's been hired in May last year, and that has been working on that. We now have a prototype of something related to trajectories that we're going to present very soon. Okay, then another thing that I'd like to mention is we have connection with different partners. So for instance, this is the ICTP experimental materials database, HTM, from Los Alamos or anyway, so I will mention it afterwards. So basically what they're showing in that paper is quite interesting, and that's perfectly in line with what Alessandro was saying yesterday. So you see that when we have a lot of data, okay, so that's here, we have not very much information. I mean, we have the structures, but very little is known about the properties. So if you want to move in this having more properties, you can go to something like Landau and Bornstein, so encyclopedia, where you have a limited number of data, but many properties. When you are in journal articles, there's a lot of information, but sorry, a lot of properties, but not very much data. So we'd like to go in this direction. So, I mean, the database that were created from ICTP calculation is a big step in that direction to be able to have both data diversity and a data size. Okay. So in that paper, yeah, we have connection also with some non-open source or some commercial databases, the one of ANSYS, the one of the polling files, and we have connections with NIMS as well. So this HTM, if you look at it on the website, see it's from the NREL, not from the other one that I mentioned, okay? So in that database, you have, a lot of information about some experiments. So this is just a TSNE, which is some way to treat the data. And they have their own specific API. So we're trying to convince them to also adopt the Optimade API. Another one, which is very interesting, which is an initiative that is called Starry Data. You may be interested by this one. So it's a website where what they did is, as I showed in my previous slides, so there's a lot of information in paper. So what they are doing is that they are screening automatically the paper and trying to create a database where they extract the information from the experiments. And so they have also their own specific API that you can use to query their database. And again, we have contact with them. They've been participating to some of the workshops to try to interface to Optimade at some stage. So there's a lot of work involved. So another thing that we think is important is what is called ontologies, because that's a way to translate things from one database to another in terms of definitions. And so we are interacting with people from ontologies. We've had a workshop in last October, and we are trying to improve the links that we have with other initiatives such as the EMMO. And then I would like to mention a workshop that's going to take place both in person at the SECAM and online, so you'll be here, and where we will be focusing, on the point that's sustained by the SECAM, which is the molecular dynamics and the biosimulation, and also we would like to develop in the longer run a platform for fitting machine learning to the potential. And this is done in collaboration with Colab. And so with this, I would like to thank the list, all the contributors to our initiative, and I'm ready to answer all the questions. Thank you very much for your attention. Okay, 1, 2, and 3. Okay, 1.
Sorry, thank you very much, sir.
Maybe you should come closer to or maybe I will repeat the question.
Okay.
I will repeat.
So my first question is this database, is it only data for material science that is available there, or any kind of compound?
So databases that I mentioned so far are indeed for materials, okay? But as you have seen maybe from this slide here, there's a move towards biosimulation. So now we have interaction with another database that is called BioExcel, where they store trajectories for biological systems. Okay, and we have had good interaction with them, and we hope to be able to release something in the coming months where they will be involved as well. Okay? But still, I mean, it's a limited scope, of course. We slowly try to improve, but of course, I mean, when you have diverse things, having a common API is even more difficult. Okay. Yes. I'll get back to you afterwards. Let's give a chance to everyone. Yes.
The first one is all these codes are open source.
Yes.
Okay. The second question is that you say that you still developing these queries to adopt complex structures like layered structures, interfaces, something like that. So is it accessible or it's still in the
No, it's still in the plan for the moment. Okay. Yes.
I would like to know all those, all those databases, are they in scale?
Are they in there?
Scale, like if you want to work more than one.
Databases, if you want to work with more than one machine.
Yeah.
What do you mean? Sorry, I don't understand the question.
You mean the scalability of this database?
I don't understand what is the scalability of a database. What do you mean by the scalability of a database?
Like if you want to work with more than one.
More than one. One PC.
So,
I mean, a database can be interrogated by many PC at the same time. It just depends on the bandwidth and so on. So, I mean, they're not doing. I mean, the database. Okay, there's two things. One is how you populate the database, and there you need machines that, with codes that need to be scalable in such a way that you can do a lot of calculation to populate the database. But then once you have a database, it's just data, and so many PC can interrogate it at the same time. It just depends on the bandwidth of the internet. Okay. Yeah. Your first one.
okay.
And I'm sorry, I forgot to repeat the questions, and I will try to do it.
Another question I have is in terms of accessibility to the databases. You mentioned that you can query the database, and I want to know, is it that all these databases that you mentioned, that once you throw a query, the query will be able to access all of them?
Yes.
And get what you want.
That's what I showed you with this example.
At the same time.
When I showed you this example here,
okay.
Do you remember? There was one query, well, at the same time. Okay. Of course, you do things one after the other. You're not bombarding over the database.
No, I mean,
you do one, then another one,
yes,
then another one.
To fish out all the
info. Yeah. Okay. This is what I showed you here. Exactly.
Okay.
Okay.
Thank you.
Yes, question.
Thank you. I need some more about why query database. What are the elements or parameters to direct me to create my data file when I query? What parameter should I direct me to take elements in databases?
Okay, so the question is,
what amount of data should I need to start to build my data frame for a machine learning?
Okay, there's many questions. So the first one is why query databases? Then is what are the parameters that one should query for? And then what is the amount of data that is needed to start something, let's say locally. So why query databases? Because you're looking for something. I mean, it's one of the things of FAIR is to reuse the data. As I was showing my kernel, some of the data has been thrown because it was not useful for the application that was targeted in the beginning. But maybe that thing there is useful for you. So why query is to see if there is something useful for you. It's just that. So you have data that has already been computed. It's there, open for you. You just need to look and see if there's something useful for you. Maybe there's nothing, but maybe there's something. And if there's something, you don't need to redo it because it's already been done. That's the whole point. Okay? Does that answer your question? about the queries. Why queries? Yes. Okay. So the idea is really to not repeat calculations or experiments that have already been done. If it's already been done, let's use the data that's there, especially because in those databases, you can trust them. Okay, it's not a PhD that did a calculation on the side and maybe didn't converge anything. Things have been tested before putting that in the databases. So it's curated data. Okay, so this is the why. Then the second question is which parameters are you looking for? I mean, that depends on you. It depends on the application. As I was showing in the beginning, for good transparent conductors, you have to know that you want a good stability, a good mobility, a band gap that's bigger than 2.2. So this is really application dependent. So this is an important part of the work that you guys have to do. That's to figure out, okay, for the application that I have in mind, what is it that I'm looking for exactly in terms of properties? Okay, the databases, they just collect the data. Then there is a work that you have to do. And that is to figure out what do I need? What is it that I'm looking for? Okay, if I want something transparent, then the band gap should be bigger than 3.2. You have to convert this transparent into a property. Okay, and so you have to think about what are my requirements? Okay, and then the third question is how many data you need to have. This I don't fully understand. I mean, do you have machine learning in mind? Yes, okay. So if that's with machine learning in mind, in that case, I mean, it depends because sometimes you can start to have a good model, let's say even with 100 points. You can start to have something decent. Sometimes you need many more points because it depends on the accuracy that you want to have also. Okay. The bigger, the larger the amount of data, the more accurate your machine learning is. Okay. This I will show you in my second talk. Yes.
So Gian-Marco, I had a problem. I told you before. Even with Optimate, the first part of the core of the query is different for different.
Yes. Yes.
Is there a way to synchronize it? Like maybe you set up a tiny URL that is fast to point to the different.
That might be, but as I was showing you, there is this this thing here where if you go to /optimate providers for any of the databases, you will find what's the first part. You can do that automatically. I mean, I don't have the power to convince all these databases to change it. But maybe indeed you're right, and you could create a tiny URL for.
Yeah, that will just do that.
Okay, we can think about that. Yeah. I mean, you can do it yourself actually. Yeah. Tiny URL is open. So. Other questions here? Yes.
It's the way that the database collects the data and organize has something to do with what I'm explaining yesterday. This whole dimensional reduction.
So the question is about the organization of the databases, if I understand correctly, and if there has been already some clustering in there. I think the answer is no. It's you just have raw data. You have the raw data, and then you have to do the clustering if you want, because you can do different kinds of clustering. I mean, here you just have. Typically, you will have a CIF file, so the structure, and then some property related to it.
The way that is related to the unrelated to that.
No, and even I mean, here I'm showing you. I'm speaking about Optimate, which is one way to query the database. But the internal organization of the database is very database specific. We don't ask them to change their organization. They organize as they want. But all we ask them is, if we ask you something in this way, this is how you should respond. And this is what they do in such a way that you can ask all the databases, whatever the way they're organized inside, you can ask them the same question and they will reply in the same way. Okay? So the organization of the database is really database dependent, and we're not changing that at all. It's really an external layer. Yes, please.
Is there a way that, like if I'm using two databases to do a machine learning, possibly because I want to enlarge the number of like to make it large. Is there a way of filtering with similar structures that are common to data, like project? So how do I filter this one such that I can add and have large data?
So this is an important question indeed. I mean, I can tell you one where I know of. So in Biomagen, that was presented yesterday by Anubhav, there's something that is called a structure matcher. Okay, so if you use the structure matcher, you can compare two structures and see whether they are the same with a certain tolerance, of course. You have to define some tolerance on the positions, on the angles, and so on. Once you have defined that, this structure matcher can tell you, yes, they are the same or not. Okay, and as a result, you can decide whether you want to add that to the design. Okay. Yes.
You are saying that the database or the data should be fair. Does that mean any researcher or anyone can be able to access the data and maybe publish from it? And if that is the case, how do we acknowledge or reference such a database?
Okay.
That is one question, please. The next is from the different database pieces, you have also mentioned we have like the National Research Labs, you have mentioned ANSYS. Is there a way they work together so that we could avoid much of competition, such that when we have data, I don't have to go to this database, I go to this and I find the same information.
Okay, so for the first question, so the first question is about the fact that I mentioned that the databases were fair, so can they be used? So all the databases that I showed here were open databases. So as soon as the database is open, you can query it and it's open. So how to cite it? Just usually, if you go on the website, they tell you how to cite it. Okay, so typically the website will have a section about, and then when you go to about, they will tell you publication, cite me in this way, and stuff like that. Okay? Okay, and indeed, the point is to reuse the data. So reuse it. Okay. Here, the Optimate is more about interoperability in the sense that you can query the different databases in the same. Okay, and the findable because of the providers, even though the beginning is different as was pointed by Omarulu. Here we have a way to find the different databases. Okay, and it's accessible because you can query. Okay. Now regarding the second question, I mean, besides those databases that are open, some of the databases are not open. I mentioned ANSYS, I mentioned NPDS, which is not open. Okay. I mentioned NIMS, which is not open. But I think that, I mean, okay, that people can make a business out of the data is something that we have to accept. Because as was mentioned by Alessandro, curated data is gold. So people can make business with that until the moment where other people provide the same information for free, or similar information for free. Then they will go out of business. Okay, but we have to accept that. Okay, and then I forgot your last point. It was.
I was asking about kind of synchronization.
Yes, the synchronization. Yes. So the question is about, is there a way to synchronize the database? I mean, people are independent, so they can do whatever they want. I mean, it's just your job to make sure, as I was just pointing here, to make sure that whether or not it's the same structure. It's not so complicated. You can do that automatically. You run through all of them. Say, is it the same? Yes, no. If not, I'm going to add it to my database.
Okay, Gian-Marco, there's some questions online.
Okay.
So you have mentioned lack of important property values for all known organic compounds. Is there any focus by database repositories to fill the gap?
I mean, we have seen yesterday from the talk of Anubhav, and I was showing you the things. Yes, there are efforts, but as it takes time to compute those properties, it's difficult. Okay, and I will speak about that in my second talk about machine learning. I mean, one way to fill the gap is precisely machine learning.
But Gian-Marco, it's not it's a computer that. So why is it?
Because it costs money. I mean, yeah, you know, you heard the numbers from Anubhav yesterday. It's millions of CPU hours, you know, literally. Okay, I'm going to show you later on something about phonons, where we computed 1,500 phonons, which is nothing. Okay, that's 6 billion hours of CPU. Yeah. Yeah, it's CPU time. I mean, you have to relax the structures. 6 million. 6 million. But still, I mean, it's an amount of money. You take choices about what you feel and what you don't feel.
So let me ask you another question. There's another question there. So similar, I've seen all these data for inorganic materials. Is there any database for chemical organic materials and solvent or for polymeric materials?
I think there are a few. I've been aware of some. The question is, are there some databases? So these databases that I mentioned are about inorganic materials. Are there databases for polymeric materials, polymeric crystals? And so the answer is yes, probably. I've seen a few of them, but that's not my field of expertise, and so we try to establish some connection with some crystalline organic databases. So they came to one of the meetings, but then, I mean, we can afford the people to do the work. So yes, there are some databases you have to search and find if at some stage they want to interface with Internet. I mean, we can only propose people to interface, but if they don't want to, we can afford that. Okay.
Any other questions? Oh, no. Oh, Ibrahim. Yeah, Ibrahim has a question.
Yes, sir.
Yes, please.
Hello, sir. All right. My question about this REST API. As you mentioned, the essence of this REST API is to query several databases at the same time. And as we know, these different databases has their different structural architecture. My question is, when querying, say, multiple databases at the same time with a particular properties of interest, say you want to query a database with, say, transition metal, with the specific, say, band gap or say formation energy, for instance, and it happened within such a database that you query, one or two among them has no such a properties. What will be the response from this query? Will it be a good response? Will there be an error, or what will happen?
Can you repeat the end?
Hello?
Can you repeat the end of the question? I didn't get it.
Okay. The question is, when querying multiple databases at the same time,
yeah,
and what you query as a property, for instance, you want to search for transition metal with a specific property, say, searching for transition metals, a range of band gap or formation energy. And within such a databases that you query, let's say you query for 10 databases, for instance, and among these 10 databases, 2 or 3 among them has this transition metal, but does not have either the, say, band gap or formation energy, which you are querying for. My question is, what will be return of your query? What will be the response? I mean,
let's make sure that I understood correctly. So if you query the databases and some of them have the band gap, but not the formation energy, or
the exact question is, if you query a database and what you are querying is not part of the, say, attribute of the database that you are querying.
If it's not part of the database, you cannot query. I mean,
no, what I mean is, for instance, in some databases, you have a lot of properties. They have band gaps, they have formation energies, they have density, a lot of them. And in your search, you mention one or more among these properties. And it happens they have one, but not all of them. So will it ignore or will it return the one that it has?
I'm sorry, I don't get the question. So if you're querying for something that's not in the database cannot return anything. You know, if you're searching in a drawer for something that's not in the drawer, you will find nothing. That's all I can tell you. I'm not sure that I understand. So do you understand better what you mean?
Okay.
If there is no transition metal there, you cannot get an answer from that database.
No. The question is not exactly like that. I don't know how to put it. For instance, now, let's say I want to query through, let's say, material project.
Yes.
And let's say plus material project and let's say COD, cross-geographic object database at the same time using REST API.
Yes.
And I want to search for, let's say, formation energy and band gap within a speak. This profile I want to search for a speak organic compound. Organic compound.
Okay, and then what?
And it happened that, let's say, in COD, I have the this compound. It only have the band gap, but it doesn't have the other property. Let's say the formation energy, which assists band gap and formation energy. But okay,
it doesn't have it. What can you do with that? I mean, if it's not there, it's not there. I don't know. Yeah, I mean, if it's not reported, what can you do?
I'm sorry. Maybe I will put it into writing. Maybe it will be much understanding. Yeah. My second question is this again. Sorry. I have some cases where I have literature reporting that the machine learning can perform better than the DFT. Is it true that trained data set can outperform the original data set?
Okay, I'm going to repeat the question. So can machine learning do better than the original data set? That's the question?
Than the original.
Yes.
Do better compared to what?
DFT.
No, but I mean, if compared to what? If you're better than DFT, you are better than DFT.
Of course, the experiment, because always the experiment is the main.
So, I mean, it's just by chance, because, I mean, a machine learning is meant to reproduce what is being trained on, okay? So if what you're training it on, say, for instance, the band gap, you take the PV band gap, okay, and you say, okay, I compute the PV band gap with DFT. Of course, there's a different respect to experiment. We all know it, okay? So if you do a machine learning and it improves with respect to experiment, that's pure chance, okay? It's meant to reproduce the DFT, not the experiment.
Maybe you learned because
no way.
Too many material.
There's no way, unless unless you provide it, and that exists. There's something that is called multi-fidelity. There's a paper by Schwepping long about that, where you provide both DFT and experiment, okay? And you try to improve the prediction that you have compared to just using experiments. In that case,
so you can blend the two to train your model.
In a sense, yes, you can try to blend things.
Let's think about it. You have to get some property right because of classification of the nodes. So let's say the machine learning want to include some classification of the nodes. Do you think this is possible?
I mean, it's possible, but it's not meaningful. It's not meaningful because, I mean, a machine learning is only meant to reproduce the original training set. If by making a mistake in this reproduction, because that's what you're doing, because you say that you had an original data set, and then you have a correction with respect to that, it improves compared to another data set that's pure chance. Unless, as I was mentioning, you have the first data set, which is the DFT, then the experiment, and in some way you manage to take advantage of both of them to improve the prediction on experiments. This is a different approach. But if you didn't have the experiments, improving compared to experiments based on DFT, that's pure chance, and I wouldn't trust that.
Okay, thank you.
So let's thank Gian-Marco once again. The next talk will be by Professor Matthias Jeffler. He's going to come right now, and I'm going to see how to connect. So,
How do you stop sharing here?
Okay, first.
Here. Okay, should I unconnect here?
No. Let me try to see if I can connect him. I'm connected to the other person.
I can still use it.
Yeah.
If you want.
Oh, no.
Hello. Is it already my turn, or where are we at the moment? I cannot hear anything.
Hello, Matthias.
Yes, hello. Can you hear me?
Yes, but please hold on. Okay, can you try again? Hello, Matthias.
Yes.
Okay, we can hear you. Can you hear us?
I can hear you now, yes, but you were away for a moment. Okay.
Okay.
And can you see the screen already?
Yeah. Yes, we can see the screen. Yes, we can see the screen.
Okay, so then I can start, is that right?
Yes, correct.
Okay. Yeah, good morning. Thank you for having me here. So the title, as you see it here, is Learning Rules. Actually, let me just see the pointer. Learning rules for materials, properties, and functions by artificial intelligence. Some of the things which we just discussed, I think, in the last talk will be touched here again. So there are two terms which are important here. And because they also address a significant advancement or a change of the way we have been doing science so far. In data-centric material science, we accept that many aspects of materials and of the function of materials are not necessarily described by laws that can be written down as a differential equation, like, say, the Schrödinger equation or Newton's law. And we accept that there's more than equations. And the title, therefore, actually says learning rules. And I hope that at the end of the talk, you will understand what I mean. It means rules, not necessarily laws. These rules depend on parameters that characterize the material. These parameters do not necessarily reflect a microscopic mechanism directly, but they are more like genes in biology. And that's why I call them materials genes. Again, I trust that by the end of the talk, you will understand what I mean and why this is an important concept, different to the way we have done work in science before. Now, in my earlier talk in February, that is, I think, at least available on YouTube, maybe also on your website, you can see why we call this data-centric research the fourth paradigm of material science. And this is also described here in this paper, on this chapter, on this handbook by Claudia Draxel and myself. Thus, as we said before, we don't necessarily search for scientific laws in terms of differential equations, but we search for correlations. This concept that there are relationships that do not go beyond laws and equations will change the way how science is done today. One additional challenge we are facing in material science is that we have a noticeable amount of data, but in these different databases, which have been mentioned, but the materials that are useful for a certain function, for example, for a catalyst or a photovoltaic device, are very few. The high quality materials, that is the useful materials, are statistically exceptional. Let me remind you about a textbook example. So let's assume that we are looking for a material that has a high optical transparency. At the same time, the material should be a very good heat conductor, and the material should be robust and hard. So from the infinite number of possible materials, there's only one that sticks out, one that is clearly leading in these three requirements, just one, and this is carbon in the diamond structure. This is what I mean by statistically exceptional.
So, Matthias, are you advancing your slides?
Sorry?
Are you advancing your slides?
Actually, in a moment, yes.
Okay.
But you see now the big data and statistically exceptional materials?
Yes, yes.
Okay, so the next will come in a millisecond. Thank you. So the number of materials is practically infinite. Now, Gian-Marco has said, actually, we know about something like, I forgot actually the number. I think the way I know it, I would say we have crystallized, or we have some knowledge about 250,000 materials. But if you consider all the 100 atoms of the periodic table of the elements and all possibilities of mixing these atoms in all possible structures and unit cell sizes, implies that the number of possible materials is practically infinite. We know very few, and from this very few, we know just 1% of the properties. But in principle, it's not just very few, it's not just 200,000, it's practically infinite. This implies that it's very likely that materials exist that we don't know so far, and that have novel properties or a performance in their function that is better than that of the materials we know to date. Or it may be that some of the known materials have properties that have not been recognized so far. So how can we find these exceptional materials? As discussed, we can get information from high throughput experiments or high throughput computations. But in view of the sheer size of the chemical and structural space of materials, this direct information will remain very insufficient. That was some of the questions, is that there's still actually a big gap between what we have and what we really need. So the daunting challenge for artificial intelligence, for material science, is that in this practically infinite space, the interesting materials are very rare. The interesting materials, that is the materials with a high performance function, are statistically exceptional. A route towards solution is the creation of maps of materials properties. These maps rely on the knowledge of the appropriate coordinates, here called descriptor D1 and descriptor D2. These are physical parameters, but they are initially not known. Only if we have found the appropriate descriptors, we may discover such a map where in a relatively small area, we find systems which are good superconductors, and in another region, maybe systems which are good for photovoltaics. In my talk, and so if you have these regions, then we can zoom in and find better materials. In my talk, I will show our first steps, how this coordinate system, that the two or more descriptors of such a map can be found by artificial intelligence. Let me emphasize this crucial step to find the appropriate descriptors again. So if you just have a target property, that could be, say, the band gap or the heat conductivity, and you list that as a function of some coordinate, let's say the time when the calculation was performed. There is no structure, obviously. These are just data. But only with the right descriptor, we will be able to uncover really the correlations and the systematics. So if we have found the descriptor, then we see some structure, and then we can do machine learning, and which is nothing else than fitting or interpolation. So then we can do machine learning and getting maybe a better insight. So the key intelligence step is the identification of the descriptor. Now there's another thing which is actually interesting in the sense that which is very trivial, I would say, but it's still very often forgotten. If you want to do machine learning or artificial intelligence, you need data, obviously. But you should not underestimate really this work. The data collection, the data management, that means actually getting good data. We call this very often now clean data, and clean data means data which are fully characterized. Only if data are characterized, if you know what has been measured, if you know what are the approximations behind the calculation, the data are useful. This is the step 1 and 2 should not be underestimated. It's very important work, and we should really give credit to people who do this work, and everyone who's doing machine learning has to do this. You also have to, and only then you can really do the data analysis, which still actually is complicated, and you can start interpreting your results. But keep in mind, artificial intelligence is stupid. It will only work with what you give it, and if you give it the bad data, it cannot give you anything useful. Here is the landing page of the Nomad Artificial Intelligence Toolkit. All the examples that I will describe now, and many more, can be found there in terms of tutorials, videos, and Jupyter notebooks. The idea is that users can reproduce published results, and they can modify the notebook for their own research. This is an open activity driven by the academic community. The Nomad AI Toolkit offers several tools, and Luca Giringelli will explain this in the next talk. And he will also demonstrate it in the hands-on session in the afternoon. The examples that I will discuss in a moment, and many more, can be repeated and modified on this webpage. So we have looked at several systems and several functions to build maps of materials properties, to fill the gap between the data which have been calculated or measured and the data of systems we don't know yet. The role model for our ideas was and is largely the concept of the periodic table of the elements. Mendeleev knew about the existence of about 60 atoms, 60 atoms, when he was doing his work. And he knew some of the chemical properties of these 60 atoms. But with his table, he could predict the existence of other atoms, and he could even predict their properties. Ashby plots in engineering are another role model. So we want something very similar. Based on a few data points, we want to have a map which really tells us about the other data points, which we have not really found yet. We looked into many systems already. So we looked into, say, crystal structure prediction. That is here the top left. For example, octet binaries. I don't tell you really what the X and Y axis are on this schematic plot, but the X and Y axis of this blue-red plot are just atomic properties. There's no information about a bulk solid, just atomic properties. And if these two descriptors, for example, point into the blue region, then the prediction is, or the message is, this will be a system which crystallizes in the rock salt structure. If the descriptor points towards the red region, the crystal will be a zinc blende structure. Now we looked also at other systems. Group 3 oxides, so aluminum, gallium, indium oxide. stability and band gaps. And here, I just like to mention, we also did what is a machine learning competition at this machine learning platform called Kaggle. That was very interesting because within 2 months, 900 different groups were working on our data, coming up with different machine learning models. There's a publication, and if you're interested in this machine learning competition, you can read about it. This is a very interesting new class of materials, very promising for a new type of, say, semiconductor physics and technology. We also looked at perovskites. There has been a Goldschmidt tolerance factor, very famous factor which tells about the stability of these systems. With our methodology, we could determine a related but different factor, which has a much higher reliability. So using data from the literature, we really have now a modified Goldschmidt factor, I would say, with a very high reliability. We looked at the activity of carbon dioxide, and I will talk about this actually in a moment. We looked at classifications, topological insulators, finding different maps where there are trivial insulators. And we looked at classification, asking, can really the atomic properties tell us if a system will be metallic or insulating, or how much actually we need to tell about the structure. We have developed 2 different methods for these questions, the subgroup discovery approach and a method that we call SISO, Sure Independence Screening and Sparsifying Operator, which is a combination of symbolic regression and compressed sensing. So let me describe these methods because they are really very powerful for this goal of pattern or map discovery. So the goal is pattern discovery in data, pattern discovery for uncovering physical characterizations. And this means that we need to also achieve some understanding. We don't want just really a general machine learning, but we also like to achieve some understanding at the end, to have an idea what should we change to find a better material. We like to identify descriptors that are explainable or interpretable. In this tutorial picture here on the left, I plot a material property as a function of some material descriptor and just a few data points. Now, standard machine learning employs what is called a global model, that it uses some single model to describe the whole population. So in this needle in a haystack example, it tries to fit the hay and the needle with the same model. It therefore minimizes the overall prediction error using regularization. This means that we disregard local details on purpose. We don't want overfitting. Thus, with these gray data points and using a global model, here a linear regression, the best fit looks like this. Now, the first method that I like to advocate in my talk is, I mentioned that already, subgroup discovery. And I'd like to acknowledge Mario Bolai and Yildiz Freken, who have introduced us to this concept. The point is that there are maybe more information behind these points. The points may be, say, red and blue. But they may be red and blue, but we don't know that. Still, we hope that artificial intelligence can help us to find out. So, but if this is the case, quite obviously, I would say the meaningful fit would be like this. There are 2 distinct subgroups. This is the science we like to recover in the data. And with this, we also will get a better and meaningful description. In this case, the description is even orthogonal to the global model. As I said, we may not know that the data points are red and blue, but we hope that AI will help us to find out. And here is another tutorial picture for the same problem. Now addressing the point that we are interested in materials that exhibit statistically exceptional behavior. These here on the right are 1,000 data points. And now we have 2 descriptors, x-axis D1 and on the y-axis D2. And we have a property Y, noted here. That means actually the data points can be square or circle. Now, how can we find structure in the data? If you look at it, you may be able to identify something immediately. Here is a region where you have only squares, for example. Obviously, we want that such identification is achieved automatically without really the need to plotting, because very often you cannot plot things in 2 dimensions. So let me emphasize that this pattern is also only visible if you plot the data as a function of these 2 descriptors. If you would use other descriptors, the structure will not show up. Thus, we need that the coordinates, the descriptors, are found automatically. And this is what subgroup discovery is doing, finding the coordinates and simultaneously finding the patterns. In more mathematical words, we like to find Boolean conditions. So we find Boolean conditions, also called selectors, which may be combined into a conjunction. So we check the whole data set and ask if with these descriptors, D1, D2, or with other descriptors, D4, D3, D4, and so on, if there is really a certain structure in some Boolean conditions. Now, and we do this by maximizing a quality function which addresses our target property. So here it could be having a maximum of squares, but it could be also in physics, say, having a certain band gap of a material. This quality function needs to be defined by us because we want a subgroup which shows, say, the best superconductors, or we want a subgroup which shows the best photovoltaic systems. So this quality function is choosing the property of the subgroup that needs to be defined by us. However, the Boolean conditions and the coordinate systems are not defined by us. They will be defined or identified. They will be identified by subgroup discovery, by the subgroup discovery procedure. So for the tutorial figure here, I noted 3 subgroups here already: sigma A, sigma B, sigma D. D1 should be in this range, and D2 should be smaller than 0.9. This is subgroup A. And now actually, let me just show subgroup A and B. So subgroup A is the one which we mentioned already. Subgroup B is something similar in just having circles. A and B are 100% pure subgroups, but of course there is no need that you ask for something 100% pure. You can also say, I want something which is dominated by squares, and that is subgroup C, again, defined by these conditions here on the bottom. In these ranges, this is the definition of the square. So subgroup discovery identifies the best coordinates, and it identifies the Boolean conditions for the subgroups. Now, what is a good quality function? Actually, there are several ones. One which is very often a component of a quality function is the so-called information entropy, where P here in this equation, P is a probability to find a certain value that is circles in the subgroup. Simply speaking, P is the percentage of circles compared to all data point in the subgroup. And this probability is then multiplied by the logarithm of the same probability. And here you see the entropy plotted. If the subgroup is 100% pure, that means say 100% circles, for example, the entropy would be 0. It would be 100% squares and 0% circles. It is also actually 0. It's here. And in between, it just has this condition. So we want to maximize the entropy, the information entropy, to find the best subgroup. This is just one example of a quality function, and there are many more. So let me demonstrate this, what I just have said, in a specific and realistic study. Turning greenhouse gases into useful chemicals and fuels. This work was done together with these gentlemen. CO2 is typically considered a bad gas. However, I'm pretty sure that at some point CO2 may well be an important raw material for creating fuels and valuable chemicals. as indicated here. There are direct routes starting from carbon dioxide, transforming it with hydrogen into methane, which can use for fueling cars, driving, for heating, for cooking, and for many chemicals. You can also create methanol and many other chemicals. This is possible already today. It's described in this paper here. But at the moment, this is very inefficient. We need more efficient catalysts for this reaction. And I'd like to show you how subgroup discovery may accelerate the process to find one. So we have looked into metal oxides because these are typically cheap and they are typically stable. We looked at the stoichiometries noted here and we considered, metal oxides, say AbO3, AO, BO2, and so on, where the A and B, the metals, are magnesium, calcium, strontium, barium, and so on and so on and so on. These are many systems if you combine them in all these different stoichiometries. Now, catalysts happens at surfaces. That means we also considered the various surfaces of these materials. So how can we find which surface and which material is a potentially good catalyst, and therefore should be studied in more detail? There are not many experimental results available in the sense of clean data, that means in the sense of well-characterized data. Therefore, we had to do it by theory, and we decided not to calculate the full catalytic process. Now, we have studied and calculated the full catalytic process in the past, but we have learned that many aspects that rule heterogeneous catalysis are so intricate that a full theoretical description does not make much sense. So this is actually an example of what I meant earlier by the fourth paradigm that we discussed. There are processes which are so complicated, you will not be able to evaluate it directly. And you cannot really describe it in the terms of the known equations which we have. There are so many aspects which really play together. And therefore, alternatively here, we first asked which material activates carbon dioxide. The concept of activation is well established. Carbon dioxide is bad for the atmosphere because it's a very stable molecule. A stable molecule needs to get prepared for the desired chemical reaction. In the gas phase, this is achieved by charging the molecule. And charging a carbon dioxide molecule brings it from a linear shape to a tilted form. This is an indication of charging. In this case now, the carbon dioxide molecule is happy to do a chemical reaction. So the idea in surface science was very similar. That means we need a material where when you add a carbon dioxide, the carbon dioxide adsorbs, but it adsorbs in this type of geometry with a tilting angle here, reflecting most likely that the system is chemically active. So surfaces that promote such a geometry may be a good catalyst. Other surfaces don't need to be considered. Now, in our study, we looked at activation with less prejudice, and we considered 5 different scenarios that may be indicators of a weakening of the chemical bond. Because this is what you want. Carbon dioxide should bind to the surface, but it should bind in a way that the CO bond is weakened, because only then the oxygen of the carbon dioxide will make a chemical reaction. So an alternative idea, in addition to the OCO angle subgroup, would be the bond length. If you can say the CO bond length has increased, that also obviously is an indicator of a weakening of the bond. And that would be another subgroup. So the subgroup discovery analysis for this system now goes as follows. So we first define the target property. So let's say we choose target number 1. We like to find the subgroup of materials for which the adsorbed carbon dioxide will develop a small OCO angle. Then we have to define the quality function that should be maximized. And so this is what we did. So this is the quality function. We start with a cutoff because we say actually we only want to consider systems where when they bind carbon dioxide, the CO2 angle is smaller than 132 degrees. That is somewhat just an estimate. I mean, we played with different, it doesn't matter too much if it's 130 or 132 or 135. We then want that the subgroup, S is the size of the subgroup, X, and S of Y is the size of the whole data set. We want that the subgroup is not too small, so we want to maximize it under the other conditions. We want that the angle is different to the gas phase angle, and we want what is called the Sabatier principle. The Sabatier principle is a very important basic principle in catalysis. It tells that a material should bind the carbon dioxide in this case, but it should not bind it too weakly, because if it's bound only weakly, it will not stay on the surface, but desorb at higher temperature immediately. It should also not bind it too strongly, because if it's bound too strongly, there's no reason that carbon dioxide would do another chemical reaction. So Sabatier said it should be in between. And for the Sabatier principle, we used the information gain entropy, which I discussed earlier, asking that the absorption energy should be in this somewhat range, which you see here. So now we have a condition. And for subgroup 2, for the bond lengths, we did something essentially the same, except that where the angle alpha is written here, it is the bond lengths. We then use 46 potential basic features. So these are our basic features. You can also say the basic descriptors, which we had in these tutorial figures. We use 46 in a sense that we'd say the true one should be among them. So 46 potential basic features does not mean that they are all needed, but it's important to really offer as much as possible. It's important to offer more and not less than what is needed. At the end, subgroup discovery will hopefully find that from these 46 potential basic features, only 4 or 5 may be really relevant descriptive parameters. In simple words, we offer essentially everything that we felt it may be or it could be relevant. These basic features characterize the clean material surface. So these should characterize a material which at the end gives rise to, say, an activation of the CO2. The answer, which of the 46 features are actually important and what should be their range, is then determined by the mentioned quality function and a Monte Carlo scheme, which goes through the whole data set. So this is a numerically somewhat elaborate way, but it's actually automatic. And here is the result. These are the systems which we have calculated and displayed here, not in terms of the primary features, but displayed in terms of the two properties which we discussed, the bond angle between of OCO and the bond length. Now there's one thing, so these are, of course, carbon dioxide properties. The features, as I said, are only materials properties. You also see the gas phase carbon dioxide, which is the red line. Actually, this would be here the point of carbon dioxide in the gas phase as neutral. If you would charges, the bond length and the bond angle change according to this red line. So in the gas phase, these two quantities are strongly correlated. But on the surface, the correlation is essentially gone. Subgroup discovery identified from all the data points which we have 2 subgroups. Actually, we identified 5 subgroups, but I only really tell you 2. The small OCO angle subgroup are the blue data points, and the large CO bond length subgroup are the green data points. So you see they are essentially largely different. And these are the selectors, so these Boolean conditions, which are relevant for these properties. There is a charge of the surface oxygen atom of the clean surface. So again, only properties of the clean surface. The charge of the oxygen atom of a clean surface, M at the maximum of the P density of states of the surface oxygen, the kurtosis of the oxygen to P density of states. Kurtosis is basically the peakiness of the density of states. It's the force moment of the density of states. The maximum value of the two ionization potentials of the free metal atoms, and the minimum, the minimum value of the two radii of the homo-radial wave function of the two free metal atoms. So these are properties of the solid, of the surface, and of the free atoms. And with these conditions, we say a system which has these conditions, a material which fulfills these conditions, will promote a small OCO bond angle. And on the right, you see the selectors for a large carbon monoxide bond length. Sorry. So having now subgroups does not really mean yet that these are the relevant one. And as I mentioned before, we cannot really fully calculate all the properties, also because at the end, we don't know exactly what is this restructuring of the surface under catalytic conditions. I'm sorry for my coffee.
Yeah, no problem.
Okay, so we cannot really calculate everything, but we can now compare with experimental results. As I said, there is not many experimental results. There are just 7 good experiments, but they tell us that the green subgroup is the one. Actually, why doesn't it? Okay. It tells us that good catalyst materials are characterized by the fact that they support large CO bond lengths, adsorbed CO. So the rules noted in green. So several promising oxide-based CO2 catalysts have been suggested, and some of them are actually presently investigated. So with this study, we found subgroups, and with these subgroups, we found rules. So these are the rules which identify materials which should be considered for looking at better catalysts. And the quantities, like the minimum charge here, or the distance to the second, between the oxygen and the second cation, this is what we call the materials genes. These are the quantities which correlate with the property. We may understand why they correlate, but in fact, it's not really completely clear why they often, in all the details. It's like genes in biology. If these conditions are fulfilled, we have a very high chance to find a good catalyst. Let me now continue with another approach. I'm not sure why my advancing doesn't work anymore. Okay. Namely, CISO, finding an interpretable descriptor and a qualitative prediction by a quantitative description by CISO. CISO stands for Sure Independent Screening and Sparsifying Operator, which is a combination, as you will understand later, by symbolic regression and compressed sensing. So it goes actually in the following 3 steps. very similar as before in the subgroup discovery. We have to select primary features. So these are candidates. These are things which we offer. And again, we should offer all that may be relevant. Then, and this is the symbolic regression, we combine these features with various operations again and again. That means we take two features and add them or subtract them or square them and so on. You will see the operations in a moment. This gives us equations. And then we have a second thing when we have added them, but then again, this bigger feature space, we again add and subtract and square and so on. This gives very fast the feature space when we start with something like 20 features in the beginning, adding, squaring, cubing, sinus, exponent, whatever, and again with this new feature space doing the same operations, millions, billions, trillions of potential descriptors, functions of primary features. As these are functions, this is what is called symbolic regression. And then from this symbolic regression, we select one or two or more most important features from this pool by compressed sensing. And finding the best feature from trillions is done by, as I said, compressed sensing, and is called, and that tells us then the final important descriptor. Let me show this actually in a little bit more detail, comparing it really in terms of statistical learning, and why compressed sensing is like statistical learning, but it's also somewhat different because the goal is somewhat different. In machine learning, as we said, several people have said that, what we do is we fit or we interpolate the known data points, and we build a function P of D. The key scientific challenge is to find a reliable, low-dimensional descriptor. Now, the most popular machine learning tool is probably kernel-rich regression. There you write your function, which you like to find, as a sum over Gaussians, where the Gaussians are centered at all your data points. You choose a certain width, and you give, if you have 1,000 data points or 10,000 data points, you would have actually 10,000 Gaussians, and you would have 10,000 coefficients, and you optimize these coefficients. What you want at the end, that your prediction, your function at the data points, agrees as good as possible with the known data. In compressed sensing, you do very much the same thing. I'm sorry. But you do it with a linear ansatz. You say, my function, which I want to find, is just the product of two vectors. Descriptors, say all the possible features, times every feature multiplied with the coefficient. So that is linear in this equation, but the non-linearity, of course, if you have seen how we create the descriptors, is in the descriptor. But again, we asked that the prediction P of D at the known data points I should be as good as possible, agree with the known properties. Now, you cannot do this in a very good way because you may run into overfitting. And so what is done typically or always is one adds what is called a regularization. So this is a regularization in kernel-rich regression. It has the effect that you don't really have too much structured function at the end, but you have a smooth function. And by looking at the hyperparameters, you can in fact find the best choice in identifying the best, say, prediction fitting. You want to fit the prediction, not necessarily your training point. In compressed sensing, you do it with a different motivation. You also add a regularization, but this regularization is a so-called norm zero. Norm zero means the number of known zero elements in this vector C. That means we want to optimize this condition that the prediction should be as good, as close as possible to the known value, under the condition that most of these coefficients C are zero. So adding this penalty with the norm zero means most of the coefficients should be 0. And you can do it in a way that you really have that everything should be 0 except 1, and then you would have a one-dimensional description. So this is what compressed sensing is now, because solving this equation is an NP-hard problem. So essentially the whole field of compressed sensing is approximating the norm 0 by the norm 1. Now you will see that we are not doing this. So we, Luca Girangelli and us have started that work with the famous Lasso approach, least absolute shrinkage and selection operator. Lasso is very famous and very useful. It's using also the L1 norm. So it's doing this optimization with the L1 norm. And Luca has then added a second step where he has optimized it also with L0. But then since 2018, Runhai Ouyang introduced the CISO approach, where we in fact can do the L0 norm in a good way throughout the whole scheme. So CISO, as I said before, Schur independent screening and sparsifying operator. And now this vector D, sorry, my pointer doesn't really follow my finger word. Now actually the D can have 100 billion or 1 trillion elements. So this is a very, very long vector, D, of all the features which we have created, as I mentioned before, multiplied by coefficients, and then we look for that, hopefully finding that, or requiring that nearly all features should be 0. So feature spaces with billion of elements by Schur's independent screening and using the L0 sparsifying. Systematically, so the first thing is systematically construct a huge feature space, 10 to the 11 equations. Starting, so this is actually the first example which you have used for these octet binaries, starting with 23 primary features. These are atomic properties like the S and P and D, or S and P, the energy values or the range of wave functions, only atomic properties. And then we add them, we subtract them, we invert them, we square them, and so on and so on. So this gives 10 to the 11. And now we asked or select the top ranked features using Schur independent screening, SIS, from this publication. It's also called correlation learning. Select n features corresponding to the n largest projection on the target property. So we evaluate this matrix D, which is the matrix of the feature space. So if we have 82 elements and we have 100 billion say features, that would be a matrix which is 82 times 100 billion elements big. And this matrix multiplied with our, say, target vector, that means the results which we know, gives us another vector, and the leading terms in this new vector will be really the solution. The top one, in fact, will be the exact solution for the one-dimensional descriptor. We then continue for a two-dimensional, three-dimensional descriptor in an iterative way. Let me explain that further by demonstrating it with a recent study of thermal conductivity. Brief introduction to the physics, but then we come really to the application of this approach, which you just have seen. So we all know that heat flows from hot to cold, that is on the bottom, and it's described by Fourier's law. Kappa here, the thermal conductivity tensor multiplied with the gradient of the temperature. We distinguish different means of heat transport, namely radiation, convection, and conduction, shown on the right side. And in the example which I now discuss, we will only really consider conduction. Then, if you only consider conduction, kappa has the following components. So we can neglect photons. If we concentrate on insulators, we can neglect electrical currents. and we have the movement and vibrations of the nuclei. That is what is called then the lattice thermal conductivity. Here you see a video, which I'm actually showing since many years. This is an ab initio molecular dynamics calculation for zirconium dioxide at 1800 Kelvin. What you see here, if you look at the red balls and you watch just one of them, you will see that they somewhat vibrate, but then once in a while they jump. So these vibrations are not smooth. They are not continuous. There are these jumps. And what you see is not an exception. It's probably more typical than smooth harmonic vibrations. Obviously, this is just one important aspect, but it is crucial. It is crucial for understanding thermal transport in realistic materials, in particular in thermal insulators. Now, why is it important? For a harmonic crystal, the thermal conductivity would be infinite. So realistic finite thermal transport is caused by anharmonicity. And harmonicity means these jumps. So some words on the data sets which we used, because now we in fact looked also at experimental data. So we really looked into the literature, and there were experimental data of kappa for quite some elements, but we selected 75 materials. I told you before, you have to be sure that the materials which you use for your machine learning are clean and well characterized. 75 materials which were curated fraction of initial set from over 100 materials, removing what looked as unstable materials and removing electrical conductors. Still, the 75 materials are very different. These are 14 different binary and ternary crystal structures prototypes. So very different questions, very different systems, but we wanted to see, can we now do machine learning on this kappa? So the first step, as we said, in CISO is to define the primary features. These are the basic materials properties that may correlate with the relevant process. As I said, before the thermal conductivity, for the thermal conductivity, we are using experimental data, but for the primary features, we use theoretical data. They should characterize the material. So this is the list of primary features we are offering to our CISO analysis. The first one is an anharmonicity score, sigma A, which we had introduced about 2 years ago. This measured the anharmonicity. The second one is just a cheap version of the first one. I don't really have to go into this because at the end, it's not really very important. We then have the maximum phonon frequency at gamma, the high temperature limit of the Debye temperature, average phonon temperature, heat capacity, speed of sound, and so on and so on. So several things which characterize the clean material. And these are 17 primary features. Again, this is what we offer. And we hope that subgroup discovery, actually not subgroup, that CISO will at the end find that only a few of them are relevant. And so with these 17, we then continue in the symbolic regression and we do the operations. Now I list here 2 columns. Let's first really look at the left one, which is the standard way we have done it, but we have now here even made a generalization. So we subtract, we multiply, we divide, we take A minus B and the absolute value and so on. So from all these 17 combined with all the other ones and everything else you see is sinus, cosine, and third square root and so on. The more general thing which Tom Purcell has introduced is that he said, actually, why should I use A minus B? Maybe actually I should use A minus some parameter, alpha B, and then optimize also this parameter. This is parameterized CISO, and it's of course obviously much more general. And this is what we are now using also for this study. So in this way, we immediately very fast get, say, billions of different features, complicated functions. And here you see the result. So this is the CISO result. Oops, the CISO result at 300 Kelvin. as a function of the experimental values. And you see that CISO gives us a good correlation. I also really show here the previous, say, famous so-called SLAC model, which was based on some, say, scientific insight, was done by a rather simple equation. To some extent, we can also say a complicated equation, by some equation. And you see that CISO obviously is doing much better. Now, one thing I really like to emphasize is these plots give some idea, but they do not necessarily tell us exactly the reliability of a machine learning description. We think one should really not only look at the mean absolute error, one should also look really at the maximum error. And we plot this usually in terms of what we call violent plots. So this is called test error, but you can also say this is the error of the prediction. The error of the prediction, if you look, this is the SLAC model, the old one. If you look at the mean absolute error, the error is 0.3. But you see the maximum error is actually even 1.2. So there is really quite a spread of errors, and I think it's very important to really understand the spread. In our model, the CISO approach, the mean absolute error is reduced by nearly to the half of the previous value, 0.16, and also the maximum error is very much reduced. The widths of this violence actually tell us about the number of systems which have the corresponding error. So this is really the function which CISO finds. So as I said before, CISO finds a function from these many, many functions which we offer. And here is a constant, then function f0 and the function f1, and the function f0 is here and the function f1 is here. I don't have the time really to go through this. Again, this is the parameterized CISO. That's why we have, say, the average mass added by some alpha parameter and the mass unit and so on. So from the 17 offered primary features, at the end, there are 7, the one with the circles here, 7 which enter this equation. Again, these 7 we would call the materials genes, because they determine at the end if the system is a good thermal conductor or a bad thermal conductor. We also did some more analysis and find that, in fact, the one with the full red circles are really more sensitive and more important than the other ones, but that's not really important at the moment. So 7 genes have been identified. And then we can plot again a map. So this is the map F1 of our CISO descriptor and F0 of our CISO descriptor. Dark means a very good heat conductor. Yellow means a very bad heat conductor. And you see, I mentioned before that carbon in the diamond structure is a very good heat conductor. You see that here on the lower left side. Of course, we were interested more in finding bad heat conductors. That means thermal insulators. We were interested in finding something here in this range. And so from this type of equation, we now really did a screening, just screening of materials, where not necessarily actually a heat conductance were known. So we used 732 known materials from the materials projects database with yet unknown heat conductivity. And we find from the 732, basically looking into this map, that 91 are thermal insulators, which are heat conductivity smaller than 100 watts per millikelvin. And several of these 91 we have then tested by ab initio green cubo calculations, very expensive but quite reliable calculations, and confirmed that somewhat the prediction is correct. So this is how to use the method, doing a map, finding where are the heat insulators, and then doing a fast screening and only use a good calculation for the good candidates. So let me summarize what I wanted to tell you. I briefly wanted to tell you and emphasize again what I think several people have emphasized. We need an efficient research data infrastructure. We have some databases. We still need actually to improve on the infrastructure. Nomad, and in Germany, the Fermat project are really working on this. Nomad, by the way, is the biggest data base in the world at the moment, because we also include data from A-Flow and Materials Project and OQMD. We then want, of course, using this data for smart knowledge extraction from these complex data sets, building these maps of materials, finding where are, say, good heat conductors or actually good heat insulators. And subgroup discovery and CISO, I've shown you, can really help us significantly in this. The primary features which you identify in these methods, so we offer a lot of primary features, but then those methods select a few of it out of them. The primary features really define rules, Boolean rules, or in fact, equations in CISO. The primary features are analogous to genes in biology. They relate to the properties and the processes that they may trigger and actuate or facilitate or hinder the material's functional interest. You can look more deeply into this and try to understand that, but in general, they have really only the meaning of how you understand the effect of genes in biology. Certain genes tell you there is a high chance of a certain cancer or high risk of a certain cancer. The next step, which we started with the work on the thermal conductivity, is to incorporate more experimental data. And we have actually, I think, a key publication here, which by Lukas Fopper on clean experiments and artificial intelligence, where we explain really the challenge. Typically, experimental data are not sufficiently characterized so that you can combine them with other data in a materials database. And that is because experiments are enormously complicated. We, in theory, have it simple. We have an input file and an output file. Characterizing a sample is extremely complicated. And in this paper, we've described actually how you do this. Clean experiments means well-characterized data together with theory and artificial intelligence. And with this, I thank you very much, and I really invite you for questions and for the discussion.
Questions? Matthias, thank you for your talk. I have a few questions. I think other people will have questions too. The code for CISO, is it available?
Yes, yes, it is actually available. It's in fact in a new version, which is called CISO++. So it's a C version, and it's available. You can actually, and there's a paper describing it in JOS, the Journal of Open Software. So just look for, send me an email, or actually look for a publication in JOS.
Okay. Okay. The other question, thank you very much. The other question I have has to do with, since you have the formula for kappa from CISO, so can you just go through all the compounds in the ICSD and find the one with the lowest thermal conductivity? What's the problem?
Okay. I mean, you need a little bit more. So in this formula, what enters is not only the structure, also what enters is really some information on anharmonicity and on, let's just see that actually, CISO, Luca just really reminds us that he will actually discuss that in the next lecture. So basically, you need actually more data than just structure. You need actually information about anharmonicity and phonons. And as I think Gian-Marco has pointed out, there is a lot of data now on that, but actually still very, very little. So, but these are compared to a calculation on thermal conductivity. A calculation of with the Kubo-Greenwood equation costs actually many thousand CPU hours, if not a million of CPU hours. So you still have to do some calculations to get all the information telling you about the anharmonicity.
Okay, yeah, but so in that case, why could you just do CISO on the properties you can easily calculate? like instead of doing anharmonicity, you know, you can use MagPy to find simple properties and then use those properties for CISO. Is that possible?
No, because at the end, CISO gives you a scientific description in the sense that the genes which are relevant are really relevant for the mechanism. So you will not understand thermal conductivity if you don't give it information about anharmonicity. Okay. Right? So it's really meant as an interpretable and physical meaningful description. The equation is not physically meaningful. The equation tells you about the correlation. But the parameters which enter must be physical meaningful. Otherwise, you cannot get a reliable description.
Okay. Thank you. Other questions?
Okay, there's a question in the chat. Okay. Is it possible for calculation of lattice thermal conductivity for doped materials rather than pure materials? And the answer is yes, this is possible. But again, as I just have said, what you need to do at least a calculation of the vibrations on the anharmonicity for doped materials. But in fact, that is doable, and it's certainly much cheaper than doing a thermal conductivity. But yes, this is possible. In fact, some of the things we have done. So you know, sodium dioxide is a very good heat conductor, and we looked into and the way actually it's used, because you want to prevent a phase transition, is to dope it with yttrium. So yttrium doped zirconium dioxide. So that we have studied to some extent already. So yes, that is definitely possible and is really the way to go.
Okay. Sorry, I still have a couple of questions. So we see, since you have this formula for the thermal conductivity, I can just do a mathematical optimization to find the lowest possible thermal conductivity. I mean, of course, you could say it's 0, but someone can do that, right?
Actually, that's a good question, because actually that really points to a thing we are just really working on since the last year. The parameters which enter this equation are physical parameter. Yeah. They do not tell you directly the material. So maybe in mathematical terms, you can say the equation which we have cannot be inverted. That you can say actually, this is the material which has really these properties. So you can only really now at the moment scan for different materials and then really calculate these properties. And then you see where you are on this map. There's this orange-yellow map which I showed you. So you need a type of a high throughput screening, but of course not really for the expensive thing, but for the simple phononic aspects. Okay. But it's not yet invertible, but together with Mario Bolay and some mathematicians, we in fact work exactly on this question to have a relationship between material and this map.
Okay, thank you. Any other questions? So please, but let me ask 2 questions, then I'll stop. So can you use CISO to find reaction coordinates or collective variables? Can you use CISO for that?
To find reaction coordinates.
Yeah, a collective variable for a reaction.
Yes, I think you can. So basically, the way I would probably do this in saying, if you have a reaction, you usually actually have many reactions, right? And you want to know which is many reaction pathways, and you want to know actually what is really a reasonable pathway. You would calculate probably actually the barrier, right? Because the barrier enters at the end the kinetics. So finding which barrier, and that means also the position, and that means the pathway that you can do. Yes.
So my last question is philosophical. So should we be doing more about CISO or deepening our condensed matter theory? So for instance, in superconductivity, we don't know the correct mechanism. Yeah, maybe CISO can help us, but maybe we should also do fundamental physics to find, not use data, but think of what to do. I'm thinking back to say, for instance, if do you think, for instance, CISO could have found something about Cooper pairing, like responsible for superconductivity? Do you think CISO could do that?
I think so, yes.
Okay.
But I should really say, actually, however, I mean, CISO can identify the genes, that means actually the quantities which are relevant, but of course only if you offer them. That's why we're saying actually you should offer more than you think actually could be relevant. At the end, you will be surprised. So in the thermal conductivity, for example, you would have thought that maybe the Grüneisen parameter or maybe this parameter is relevant, but you find actually another one is actually more important. And that tells you at the end about the physics. So if you give all the properties which you could think may play a role for high TC superconductivity, and then let CISO do the description, CISO will tell you from the, say, 50 parameters which you offer, only these are really relevant. And that then gives you the possibility to look more into the mechanism which is behind that. But you have to offer, if you miss really the, if you don't offer what could be relevant, CISO cannot find it.
Okay, thank you. So Gian-Marco has a question, and then there's a question in the chat.
It's a bit a technical question, Matthias. So you showed that you have made some improvements to CISO by the introduction of this alpha parameter. So how is this parameter found? Is it an hyperparameter in this case, or how does it work?
No, it's not a hyperparameter because actually it's for every of these equations, it can be a different parameter. Yeah. It's really optimized in a more or less standard optimization process.
And it's only
and it's really very important because before we could only add quantities which have the same unit. Now we actually say alpha can have a unit, and so you actually now also really a combined system with different units.
Okay. And it's included in the distribution, right?
Yes, yeah.
Thank you very much.
How long did it take to do the CISO optimization for the thermal conductivity you showed? Like how many hours?
Yeah, I cannot say that.
Okay.
I can't remember that. I mean, that is something which we have to ask Tom, because I'm not even sure on what computer he was actually doing this. But it was actually compared to anything which we do in DFT, it's actually negligible.
Oh, okay.
So it doesn't really play a role in the CPU time my group is spending.
Okay. There's a question in the chat.
Which one? Actually, I'm not sure.
The last one. Can we use CISO to study kinetics and thermodynamics of reactions?
Okay. I think, as I said before, yes. We haven't done that yet. I mean, what you certainly can do is you can really identify barriers. But actually, I should say, I should be more optimistic. We even have done some of that. So we have done actually the kinetics of selectivity. So we have looked at the selectivity in catalytic processes, right? I mean, catalysis, you have actually two molecules which combine, but they could give this product or this product, but you only want one. And the selectivity is a kinetic-driven thing, and with temperature dependence, and on this. Actually, even on the paper which you see here, there is actually a first discussion of the kinetics of selectivity described by CISO.
Okay. Yeah. Thank you very much, Matthias. We'll be happy to have your slides also.
Mm-hmm.
So,
yes.
Thank you very much. So let's thank Professor Matthias Scheffler once again. Thank you, Matthias. So
okay.
take it now.
Thank you. Thank you.
And then we'll come back at 11:30 for the top. Okay. Yeah. Thank you.